You think you know planets, Earth, Mars, Jupiter, gas giants, rocky worlds. Maybe you heard about exoplanets, those distant things orbiting other stars. But nobody tells you what we actually found out there. Worlds where it rains glass sideways, planets made of cotton candy, a rogue world devouring 6 billion tons of matter every second, acting like a star while having no star to orbit. Diamond planets, lava oceans that stretch from pole to pole. And over 6,000 confirmed discoveries as of October 2025, each one stranger than textbooks ever prepared us for. The universe does not care about our categories. It builds whatever physics allows, and what it allows is absolutely unhinged. If you value documented astronomy and planetary science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from NASA's Exoplanet archive, updated through November 2025. The peer-reviewed journal Nature Astronomy published May 2024 on puffy planets, and data from the James Webb Space Telescope's observations published in the Astrophysical journal Letters, October 2025, on rogue planet atmospheric characterization. These aren't generic press releases. These are direct observatory findings and published academic papers tracking discoveries as they happen. Now back to the information. Let's start with the first ones we found because they broke everything we thought we knew. 1992. Alexander Wolszczan and Dale Frail at Arecibo Observatory in Puerto Rico detect something impossible around pulsar PSRB 1257+12. Pulsars are dead stars spinning hundreds of times per second, blasting radiation that would sterilize anything nearby. Yet there they are, 3 planets, rocky worlds, orbiting a corpse, the first confirmed exoplanets ever detected, and they orbit a stellar remnant nobody expected could host planets. First planet has a mass 0.02 times Earth. Second planet, 4.3 Earth masses. Third, 3.9 Earth masses, all orbiting within 0.5 astronomical units, closer than Mercury circles our Sun. Radiation levels incomprehensible. Surface temperatures wild. These worlds challenge formation theories because planets shouldn't survive their star's supernova death. Yet here they circle the ruins. Then came 1995. Michel Mayor and Didier Queloz, using the LED spectrograph at Haute-Provence Observatory in France, find 51 Pegasi b, a Jupiter-mass planet, but the orbit lasts 4.2 days. 20 times closer to its star than Earth is to the Sun. Hot Jupiters, they call them now. Gas giants hugging their stars so tight that years pass in hours. Surface temperatures exceeding 3,000 degrees Fahrenheit on the day side, 1,500 on the night. Tidally locked, one face eternally burning, the other in perpetual darkness with supersonic winds screaming between hemispheres at thousands of miles per hour. Over 1,000 hot Jupiters confirmed by November 2025. 51 Pegasi b has a mass 0.46 times Jupiter. Radius 1.9 times Jupiter because the stellar radiation puffs up its atmosphere like a balloon under pressure. These worlds shouldn't exist where they orbit. Gas giants need to form beyond the frost line, that boundary past which ice and volatiles can condense, typically 5 astronomical units out. Yet hot Jupiters sit at 0.05 astronomical units. Migration, they formed far out, then spiraled inward through the protoplanetary disk or got kicked by gravitational encounters with other planets, settling into scorching close orbits where their outer layers boil into space. WASP-12b takes it further. Discovered 2009 by the Wide Angle Search for Planets Consortium. 1.4 times Jupiter's mass, 1.9 times Jupiter's radius, orbits its star in 1.1 days at 0.02 astronomical units. Temperature 4,400 degrees Fahrenheit on the day side. The star's gravity tears this planet apart in real time. Tidal forces stretch it into an egg shape. Matter streams off in a comet-like tail. This world is dying, shedding 100 billion tons of mass per year. In 10 million years, gone, vaporized. Nothing left but a stellar memory. That's just the gas giants that stayed gas giants. Chthonian planets are what happens when a hot Jupiter loses. Named for Greek underworld deities because these are the charred cores of gas giants whose atmospheres got ripped away by stellar winds and intense radiation. HD 209458be, the nicknamed Osiris. 50 light years away in the constellation Pegasus. 0.7 Jupiter masses, 1.4 Jupiter radii. Discovered 1999 via transit method. Hubble Space Telescope observations in 2003 by Alfred Vidal-Majar's team detected hydrogen escaping at over 22,000 miles per hour. 2004, same team detects oxygen and carbon in the escaping atmosphere. This planet bleeds 10,000 tons of material per second into space. Not sustainable. Eventually, the hydrogen and helium blow away completely, leaving only the rocky metallic core behind. Core mass estimated at 30 to 100 Earth masses compressed into twice Earth's radius. Density greater than iron. That's a Chthonian planet, TOI 849be, discovered 2020 by the transiting exoplanet survey satellite. Might already be one. 40 times Earth's mass, 3.4 Earth radii, no significant atmosphere detected, dense rocky core exposed, orbits 0.015 astronomical units from its star, with a year lasting 18 hours. Surface temperature over 2,700 degrees Fahrenheit. The first confirmed Chthonian world. If the data holds, Kourou 7b was another candidate, discovered 2009 by the French Space Telescope, COROT. 1.6 Earth radii, 5 times Earth's mass, orbits in 0.85 days, temperature 4,000 Fahrenheit dayside, but arguments still rage whether this was always rocky or the stripped core of something larger. Age of the star system matters. Too young and the planet formed rocky. Old enough and migration plus evaporation could explain it. Debate continues. Now flip that around. What if the planet is big but weighs nothing? WASP 193bi, discovered by the Exotic Laboratory at University of Liège and announced Nature Astronomy. May 2024. 1,200 light-years away in constellation Hercules, 50% larger than Jupiter, 0.05, 9 grams per cubic centimeter density. Cotton candy has density 0.05 grams per cubic centimeter. Earth is 5.5, Jupiter 1.3, this world is 0.059. 50 times larger than Jupiter, but 7 times less massive. A hydrogen and helium atmosphere so bloated, the planet is basically a soap bubble, one of the lowest density worlds ever found. Only Kepler 51d is lighter. Kepler 51 system, 2,600 light-years away in constellation Cygnus, hosts 3 superpuffs. Kepler 51b and Kepler 51d studied extensively with Hubble, a few times Earth's mass, but nearly Jupiter's size. Atmospheres extended so far, they're opaque to infrared observations. Young system, only 500 million years old compared to our 4.6 billion year sun. Formation beyond the snow line, then migration inward, explains the hydrogen-helium envelope. But these atmospheres are temporary. Models show Kepler 51b will lose enough gas over the next billion years to shrink into a mini Neptune. The puffiness is youth. They're adolescent planets, still shedding their birth weight. Francisco Pozuelos, senior researcher at Institute of Astrophysics of Andalusia, said in May 2024 about WASP 193b, "We don't know where to put this planet in all the formation theories we have right now because it's an outlier of all of them. 0.14 Jupiter masses, 1.5 Jupiter radii, orbital period 6.25 days. The planet's so light that determining its mass took 4 years of radial velocity observations, tracking the tiny wobble it induces in its host star, Julian DeWitt. MIT professor and study co-author, the planet is so light that it's difficult to think of an analogous solid-state material. The reason why it's close to cotton candy is because both are pretty much air. The planet is basically super fluffy. These puffy worlds challenge core accretion models. Standard theory says you need a solid core at least 10 Earth masses to gravitationally capture enough hydrogen and helium to build a gas giant. WASP 107bi's, studied by team at University of Montreal and published Astronomical Journal, has a core only 4 times Earth's mass, yet holds a massive gas envelope. The core is too small. Something else is inflating these planets. Stellar irradiation heats the upper atmosphere, which expands outward. Tidal heating from eccentric orbits pumps energy into the interior. Or maybe they form differently entirely, accreting gas directly without building a large core first. Now, planets that shouldn't be planets at all. Rogue planets, free-floating worlds with no star. They drift alone through interstellar space in complete darkness. No parent sun to warm them. No orbit to anchor them. Just cold nomads wandering the galaxy. Takahiro Sumi's team, using microlensing observations in astrophysics, an optical gravitational lensing experiment published Nature 2011, found 10 Jupiter-mass rogue candidates in a 2-degree field toward the galactic bulge over 3 years of observation. From this, they estimated nearly 2 Jupiter-mass rogue planets for every star in the Milky Way. Przemek Maruz's 2017 study revised this to upper limit 0.25 rogue planets per main sequence star. Still billions of rogues in our galaxy alone. September 2020, Ogle 2016 BLG 1928 became the first detected Earth mass rogue, between Earth and Mars in mass, detected via gravitational microlensing when it passed between us and a background star, briefly magnifying the star's light for 42 minutes. No host star detected within 8 astronomical units. True orphan world. Nuria Miret-Roig and team published Nature Astronomy. December 2021 discovered 70 to 170 rogue planets in Upper Scorpius star-forming region, 400 light-years away, using 20 years of archival data from multiple telescopes. Jupiter mass worlds, still young, glowing faintly from residual formation heat. Infrared signatures let them spot these otherwise invisible objects. The range, 70 to 170, depends on the region's age. Younger region means brighter planets, lower mass threshold for detection. Older region means fainter planets, only the most massive ones visible, so fewer candidates. Most rogues got ejected from their birth systems. Gravitational kicks from larger planets, close encounters between multiple worlds, unstable orbital resonances. Simulations show this happens often during planetary system formation. The Milky Way could host trillions of rogues. But some rogues form on their own, not ejected, born alone. CHA 11077626, 620 light-years away in Chamaeleon constellation, 5 to 10 Jupiter masses, discovered 2008,000 mass. Observed with Very Large Telescope in Chile and James Webb Space Telescope in 2024. Victor Almendros Abad led the study, published Astrophysical Journal Letters, October 2025. This rogue is still forming. Surrounded by a disk of gas and dust, accreting material at 6 billion tons per second as of August 2025. Observations, 8 times faster than just months before. Magnetic fields drive the infell. Water vapor detected in the disk during the burst, but not before. This planet acts like a star, but isn't one. It collapsed from a cloud of gas too small to ignite fusion, but large enough to pull in surrounding matter through gravity and magnetic forces. Age 1 to 2 million years. Still infant. Estimated 1 to 2 trillion rogue planets in the Milky Way, if upper estimates hold. Nancy Grace. Roman Space Telescope launching 2027 should detect thousands via microlensing, refining the population statistics. We might be the outliers. Planets with stars might be rarer than planets without them. Then you have the terrestrial worlds that forgot to be normal. Lava planets. Rocky worlds so close to their stars that the entire dayside melts into magma oceans. K2141b 202, light-years away in constellation Aquarius, discovered by Kepler telescope, 1.5 Earth radii. 5 Earth masses, orbits in 0.28 days, roughly 7 hours, tidally locked, dayside temperature 4,900 Fahrenheit, hot enough to melt rock into liquid magma, forming an ocean hundreds of miles deep. The magma evaporates into a rock vapor atmosphere. Sodium, silicon monoxide, silicon dioxide molecules floating as gas, supersonic winds over 5,000 miles per hour. Carry the vaporized rock to the night side where it condenses and rains back down as molten droplets. The minerals then flow as magma currents back toward the day side where they evaporate again. A mineral cycle like Earth's water cycle but with liquid rock. Tue Jiang Nguyen at York University led the study, published monthly notices, Royal Astronomical Society, November 2020. The atmosphere extends beyond the magma ocean shore, making it easier to detect night side frozen solid. Temperature near absolute zero where the star never shines. Lava rains at the terminator boundary. The day-night temperature difference exceeds 4,000 degrees. No planet in our solar system experiences this. Even Mercury stays solid. Io has volcanoes, but not global magma seas. 55 Cancri A, 41 light-years away in Cancer. 8 times Earth's mass, twice Earth's radius. Discovered 2004 via radial velocity method. Orbits 0.015 astronomical units from its sun-like host star. Year lasts 17.7 hours. Dayside temperature 4,900 Fahrenheit. Initially proposed as a carbon planet, possibly made of diamond due to high carbon-to-oxygen ratio in its host star. Niku Madhusudan at Yale published Astrophysical Journal Letters. 2012, suggesting 1/3 of the planet's mass is carbon compressed into diamond and graphite layers by interior pressures. Host star has carbon-to-oxygen ratio 0.78 versus our sun's 0.55. But Johanna Teskey at University of Arizona reanalyzed the host star spectroscopy and published Monthly Notices 2017, showing the carbon abundance was overestimated. Newer measurements using more spectral lines give lower carbon to oxygen ratio. Not quite Earth-like, but not diamond-rich either. The diamond planet hypothesis weakened. Then James Webb Space Telescope observations, published May 2024 by Renyu Hu at NASA. Jet Propulsion Laboratory detected a substantial atmosphere around 55 Cancri E rich in carbon dioxide or carbon monoxide. Secondary eclipse observations during 2 separate transits showed the planet's day side cooler than expected for a bare rock world, indicating atmospheric heat redistribution. This atmosphere is secondary, not primordial. The original hydrogen-helium envelope was stripped away by stellar radiation, confirmed by failed detections of escaping hydrogen in 2012 spectroscopy and helium in 2020 spectroscopy. The current atmosphere bubbles out from the magma ocean below through volcanic outgassing. Volatiles like carbon, nitrogen, sulfur released continuously from the molten surface replenish the atmospheric gases faster than stellar wind strips them away. Planet's large size, nearly twice Earth's diameter, provides enough gravity to hold onto these heavier molecules where smaller worlds cannot. This makes 55, Cancria one of the first confirmed rocky exoplanets with a detected atmosphere, and the first to show a secondary atmosphere formed from outgassing rather than retained from formation. The surface is likely a mix of magma ocean and solidified volcanic rock, with temperatures variable due to volcanic dust clouds blocking thermal emissions. Nearly 50% of discovered rocky exoplanets orbit close enough to maintain magma oceans. Lava worlds aren't rare, they're common. Ohio State study by Kamen Unterborn published Astrophysical Journal, September 2023, modeled magma ocean behavior over billions of years. Compression from planetary mass makes magma denser than solid rock in some pressure regimes, meaning magma oceans can persist longer than previously thought even as planets cool. The minerals that crystallize out alter the remaining melt composition, which changes atmospheric chemistry over time. You could potentially date a lava planet by measuring its atmosphere. Older planets have chemically evolved atmospheres reflecting billions of years of rock vaporization and crystallization. Now the middle ground worlds nobody expected. Super-Earths and mini-Neptunes dominate exoplanet discoveries. Rocky planets larger than Earth, but smaller than Neptune. They're the most common type of planet in the galaxy, yet our solar system has none. We have Earth at 1 Earth radius. We have Uranus at 4 Earth radii and Neptune at 3.9. Nothing in between. But out there, most planets fall in the 1.4 to 2.4 Earth radii range. And there's a gap, the radius valley. Planets between 1.6 and 2.0 Earth radii are scarce. Fulton and Pettigura published Astronomical Journal 2018 analyzing Kepler data, found a distinct dearth of planets around 1.8 Earth radii. The distribution is bimodal, peaks at roughly 1.4 Earth radii, the super-Earths, which are dense rocky worlds, then a valley, then another peak at 2.4 Earth radii, the mini-Neptunes, which are lower density worlds with thick hydrogen-helium atmospheres. Why the gap? Atmospheric loss. Mini-Neptunes born close to their stars get their hydrogen-helium envelopes stripped by photoevaporation. The stellar ultraviolet and X-ray radiation blasting away the outer atmosphere. This takes only hundreds of millions of years. What's left is the rocky core, now a super-Earth. The planets that fall in the radius valley are caught in transition, still losing atmosphere but haven't finished shrinking yet. Toei 560.01 and another planet studied by Zhang and team published Astrophysical Journal. June 2025 are caught in the act, both orbiting young stars, both showing evidence of rapid mass loss, both in the valley. Give them time and they'll slide down to the super-Earth peak. Remo Byrne at Max Planck Institute for Astronomy published Nature, February 2024, with simulations, explaining the valley through 2 mechanisms. Mini-Neptunes born beyond the water snow line, where ice can condense, migrate inward. Their water ice transitions to high pressure phases under the thick hydrogen atmosphere. This water traps heat from the interior, slowing atmospheric escape. These planets stay puffy, shifting upward out of the valley to the mini-Neptune peak at 2.4 Earth radii. But super-Earths born closer in, or that migrate too close, get their atmospheres stripped quickly by stellar radiation. They shrink to the super-Earth peak at 1.4 Earth radii. Both processes evacuate the valley from opposite directions. Luque and Pale published Science 2022 studied 34 precisely measured small exoplanets around M-dwarfs and found a density gap instead of a radius gap. 3 populations. Rocky super-Earth's density 0.94, Earth density. Water world's density 0.47, Earth density. puffy mini Neptunes, density 0.2 for Earth density, no overlap. The water worlds could be planets with deep global oceans, hundreds or thousands of miles deep, with possibly ice layers below from extreme pressure despite high temperatures. Or they could be mini Neptunes with water-rich rather than hydrogen-rich atmospheres. This density gap favors pebble accretion models, where planets grow by accreting small pebbles of ice and rock rather than larger planetesimals. The pebbles deliver the water that defines the middle density population. Towai 2096 b and CE 48 parsecs away, orbiting an M4 dwarf, published Astronomy Astrophysics, March 2023. Planet B is 1.2 Earth radii, a super-Earth. Planet C is 1.9 Earth radii, a mini Neptune. They straddle the radius valley in the same system in a near 2-to-1 orbital resonance. Synchronized orbits? Planet C completes one orbit for every 2 orbits of Planet B. Dynamical interactions between them shape the system. Perfect laboratory to test formation theories because we see both planet types in one place. Kepler 11 system has 6 planets, all between 2 and 4.5 Earth radii, most between 2 and 3 Earth radii, mini Neptunes, but their densities vary widely, from 0.6 to 7 grams per cubic centimeter. Different formation histories. Some formed in place from planetesimal rings, others migrated from farther out. Same system, different pathways. Andre Isidoro at Rice University published preprint January 2025, modeling super-Earth and mini Neptune formation from rings of planetesimals at specific locations in the protoplanetary disk. Super-Earths from an inner ring near 1 astronomical unit via planetesimal accretion, mini Neptunes from an outer ring beyond 5 astronomical units via pebble accretion. The model reproduces the radius valley. The intersystem size uniformity that makes planets in the same system look similar, and the period ratio distribution. 1% of such systems might host rocky Earth-like planets in the habitable zone that underwent late giant impacts like the Moon forming event. Rare but possible. Roughly 1 Earth analog per 300 Sun-like stars by their calculations. GJ1214b, 47 light-years away. 2.74 Earth radii, 6.2 Earth masses. Discovered 2009. Studied by multiple telescopes, density suggests water world or mini Neptune. Hubble observations failed to see atmospheric signatures clearly. Too much haze, atmosphere opaque. But it's in the transition zone. Kepler 138 Oxy and DE. 218 light-years away. Analyzed by team led by Caroline Piolet, published Nature Astronomy, February 2022. Both planets have densities suggesting large fractions of their mass are water. 50% water by mass for planet D. These could be true ocean worlds with global seas hundreds of miles deep, possibly with high-pressure ice layers at depth despite being warm. The James Webb Space Telescope targeted GJ1214b, but results remain ambiguous. Eliza Kempton at University of Maryland stated in BBC interview March 2024, "We're not totally clear that we've ever seen a water world, but we have some indications that maybe we have." K218b, 124 light-years away. 2.6 Earth radii, 9 Earth masses, super-Earth or mini Neptune depending on definition. Niku Madhusudan at Cambridge announced April 2025. Possible detection of a dimethyl sulfide and dimethyl disulfide in its atmosphere via James Webb observations, molecules associated with biological processes on Earth. But confirmation remained elusive. Follow-up observations, July 2025 by Renyu Hu's team published preprint, suggests the planet may be a water-rich ocean world with a substantial liquid water ocean. The atmosphere appears to lack water vapor, which indicates a cold trap mechanism where water condenses before reaching the upper atmosphere, preventing escape to space. This would allow oceans to persist for billions of years. But biosignatures remain unconfirmed. More observations needed. The planet orbits in the habitable zone of a red dwarf, where liquid water could exist on the surface. Whether it's a water world or a mini Neptune with a thick hydrogen atmosphere over a water layer or something else entirely is still debated. These middle-sized planets challenge everything. They're common, yet our solar system has none. They span a wide range of densities and compositions. Water worlds, rocky super-Earths, puffy mini Neptunes, all in the same size bracket. Formation mechanisms differ by system, by distance from star, by composition of the protoplanetary disk. There's no single answer. There's diversity at every scale, and some planets just walk away from their stars entirely, or they orbit things that aren't stars. Eyeball planets are hypothetical tidally locked worlds where the temperature gradient from day to night creates a ring of habitability. Hot eyeball planets orbit close to their stars. The day side facing the star is molten rock. The night side is frozen solid. But at the terminator, the boundary between day and night, temperatures might allow liquid water in a narrow ring or band around the planet. Cold eyeball planets orbit farther out in the habitable zone. The day side has liquid water. The night side is ice. Liquid ring on the star-facing hemisphere, TRAPPIST. One system, 39 light years away, has 7 Earth-sized planets, several potentially tidally locked due to proximity to their ultra-cool dwarf star, Kepler. Object of interest, 262601 is another candidate. Models suggest these configurations could be stable. Life, if it evolved, would be confined to the twilight zones, where temperature allows liquid water. No confirmed eyeball planets yet, but the hypothesis stands as testable with future observations. Pulsar planets circle the densest objects in the universe short of black holes. PSRB 1257 plus 12, 2300, light years away in constellation Virgo, hosts 3 confirmed planets and possibly a 4th. Discovered 1992, these planets orbit a millisecond pulsar spinning 391 times per second. Radiation environment incomprehensible. Magnetic fields trillions of times Earth's strength. How did planets survive the supernova that created the pulsar? Did they form from a debris disk around the neutron star? Wolfsjohn's 1994 confirmation paper, Science used precision timing of pulsar pulses to measure planetary masses and orbital parameters. Planet B 0.02 Earth masses. Planet C 4.3 Earth masses at 0.36 astronomical units. Planet D 3.9 Earth masses at 0.46 astronomical units. Resonant orbits. The system is stable but bathed in lethal radiation. Any atmosphere would be stripped instantly, surfaces baked by high-energy particles. These worlds prove planets can form or survive in the most extreme environments. Then there's the theoretical extremes we haven't confirmed, but physics allows. Carbon planets could form in protoplanetary disks with high carbon-to-oxygen ratios. Instead of silicate minerals like Earth, these worlds would be carbide and graphite-rich. Interiors, possibly layers of diamond under extreme pressure. Surfaces could have lakes and seas of liquid hydrocarbons, tar or methane, no water, carbon-dominated chemistry. Titan shows hydrocarbon lakes on a moon scale. Carbon planets would do this planetary scale. Survey of 249 solar analog stars published. The Astronomical Journal 2020 found 12% have carbon-to-oxygen ratios above 0.65 dopers, making them candidates for carbon-rich planetary systems. 55 Cancri E was the leading candidate, but updated stellar measurements reduced the likelihood. No confirmed carbon planet yet, but conditions exist in the galaxy for them to form. Coreless planets are hypothetical terrestrial worlds with no metallic core, formed from fully oxidized water-rich chondrite material, where all iron is bound into silicate crystals instead of sinking to form a core, or formed when iron reacts with water to form iron oxide and release hydrogen before differentiation occurs. Sarah Seeger and Linda Elkins-Tanton published Astrophysics Journal 2008, proposing 2 formation pathways. Such planets would have different magnetic field properties, possibly none if no metallic core exists to generate a dynamo, different internal heat flow, different tectonic behavior. No examples known, but formation scenarios are plausible. Then planets we'll never see directly because distance and time beat us. Circumbinary planets orbit 2 stars simultaneously. Kepler 16b, nicknamed Kepler 16ABB, discovered 2011 by Kepler telescope, orbits a binary star system 200 light-years away. Saturn mass, Saturn radius, orbital period 229 days around the binary pair. Both stars are smaller than our Sun, one 0.7 solar masses. The other 0.2 planet orbits both at 0.7 astronomical units. Tatooine from Star Wars was fiction. Kepler 16b is reality. At least 14 confirmed circumbinary planets as of 2025. They form in the circumbinary disk beyond a critical radius where gravitational torques from both stars don't tear the disk apart. Migration inward then locks them into stable orbits. No reason why Earth-sized circumbinary planets couldn't exist, but they're hard to detect. Transits must align with both stars, orbits from our viewpoint. Trojan planets would share an orbit with a larger planet at the Lagrange, 4 or 5 points, 60 degrees ahead or behind in the same orbit. Our solar system has Trojan asteroids, but no Trojan planets. No confirmed examples in any exoplanet system yet, but dynamical simulations show they could be stable. Searching for them requires transit timing variations or direct imaging. Difficult, but possible. Then worlds defined by what they're missing. Hot Neptunes are rare. Neptune-sized planets orbiting close to their stars should exist based on formation models, but we find very few. The hot Neptune desert. Planets in this mass range at short periods, get their atmospheres photo-evaporated away, becoming smaller super-Earths, or they never end up in such close orbits because migration mechanisms prevent it. HAT-TP 11b and GJ 436b are exceptions, orbiting close, but with eccentric orbits that might explain their survival by spending less time at periastron where radiation is strongest. The desert's existence tells us about atmospheric escape rates and migration pathways. What's missing is as informative as what's there. We found 6,128 confirmed exoplanets as of October 30, 2025, across 4,584 planetary systems. 1,017 systems have multiple planets. Discoveries accelerate. TESS launched 2018 continues finding transiting planets around nearby bright stars. James Webb Space Telescope launch 2021 is characterizing atmospheres. Nancy Grace Roman launching 2027 will use microlensing to find thousands more, including rogues. European extremely large telescope coming online will directly image young massive planets. Ground-based surveys push detection limits for smaller, farther, cooler worlds. Every discovery adds complexity. The Radius Valley forced atmospheric loss models. Rogue planets challenged ejection statistics. Pulsar planets proved formation resilience. Hot Jupiters broke migration theories. Cotton candy planets defy core accretion. Lava worlds show magma ocean persistence. Super-Earths and mini-Neptunes dominate the census, yet remain absent from our system. Water worlds might be common. Diamond planets might be fiction or might be rare. Eyeball planets wait in the habitable zones of red dwarfs. The galaxy's planetary diversity exceeds anything our solar system prepared us for, and we've barely started looking. Kepler surveyed 1/400th of the sky at one region. TESS is covering 85%, but only finds planets transiting the brightest stars. Most exoplanets are too far to characterize atmospheres. Most are known only by the wobble they induce in their host stars or the shadow they cast. Direct imaging has captured fewer than 100 planets, all young, massive, far from their stars. We infer bulk density from mass and radius. We guess composition from density. We model atmospheres from transmission spectra. We theorize formation from orbital properties. We don't have soil samples. We don't have atmosphere bottles. We have light curves and spectral lines, but patterns emerge. Small planets are rocky. Big planets are gassy. In-between planets are watery or puffy. Close planets are hot. Far planets are cold. Metal-rich stars host more giant planets. M-dwarfs favor super-Earths. Everything else is variation on these trends. Systems with hot Jupiters often lack other planets because the Jupiter cleared them out during migration. Systems with tightly packed super-Earths form from rings of material in the disk. Systems with widely spaced giants grew via pebble accretion. Multiple formation pathways produce the observed diversity, and the implications scale up. If super-Earths and mini-Neptunes are common, and 1% of those systems could host Earth-like planets in habitable zones. That's millions of potentially habitable worlds in the galaxy. If rogue planets outnumber stars 2-to-1, that's hundreds of billions of isolated worlds, most frozen dying, some possibly with subsurface oceans, heated by radioactive decay in their cores, maintaining liquid water for billions of years beneath thick ice shells, cut off from stars entirely, but potentially hosting life in dark oceans. If lava planets have secondary atmospheres from outgassing, that means atmospheric evolution continues throughout a planet's lifetime, not just at formation, which changes habitability timelines. If hot Jupiters formed far out and migrated in, then planetary systems are dynamic, reshuffling over millions of years, which affects long-term stability and habitability. Every planet type tells us something about formation physics. Gas giants need enough material to grow large before the protoplanetary disk disperses. Rocky planets form from silicates and metals in the inner disk. Ice giants accumulate water and volatiles beyond the snow line. Migration moves planets from birth locations to final orbits. Atmospheric escape removes volatiles from close-in planets. Collisions between protoplanets shape final masses and compositions. Resonances stabilize or destabilize orbits depending on configuration. The final planetary system is the sum of these processes plus stochastic events like giant impacts, close encounters, and disk interactions. We learn from extremes. WASP 12b shows tidal destruction in progress. 55, Cancri shows secondary atmosphere formation. Kepler 51b shows atmospheric inflation. WASP 193b shows formation outliers. CHA 110776-26 shows rogue formation. K2-18b shows habitable zone ambiguity. Each weird planet is a data point constraining models. Each anomaly forces theory revision. The galaxy is a laboratory running billions of experiments simultaneously. We catalog the results, and the catalog keeps growing. Astrophysical Journal published January 2025 by Isidoro team offered new formation model for super-Earths and mini-Neptunes from planetesimal rings, reproducing observed features like the radius valley and period ratio distribution. Nature Astronomy, May 2024, published WASP 193b, Discovery Challenging Inflation Theories. Astrophysical Journal Letters, October 2025, reported CHA 110776-26 burst, showing rogue planets can accrete like stars. These are papers from the last year, not historical, active research. Discoveries happening faster than textbooks update. NASA Exoplanet Archive, updated through October 30, 2025, lists 6,128 confirmed planets. TESS Objects of Interest list has over 7,200 candidates awaiting confirmation. 557 have been confirmed from TESS so far. Kepler found over 2,700 confirmed planets during its mission. Ground-based surveys like WASP or HEAT-EU and KELT found hundreds more. Radial velocity surveys track thousands of stars for planetary signals. Direct imaging surveys scan young star-forming regions. Microlensing surveys monitor millions of stars toward the galactic bulge. Every method has biases. Transits favor large planets on short orbits around bright stars. Radial velocity favors massive planets close to their stars. Direct imaging favors young, massive planets far from dim stars. Microlensing favors all masses, but can't do follow-up. Combining methods gives complete picture. The weird planets aren't outliers. They're the majority. Our solar system might be the weird one. We have no hot Jupiters, no super-Earths, no mini-Neptunes. Our giant planets stayed far out. Our terrestrial planets stayed small. Our system is orderly. Most systems are chaotic. Planets packed tight in resonances. Planets on eccentric orbits. Planets that migrated from distant birthplaces. Our calm, stable arrangement might be uncommon. The violence of planetary formation typically leaves messier systems. We exist in a pocket of stability that allowed life to evolve over billions of years without catastrophic planetary reshuffling. But other planets might host life under conditions we can barely imagine. Life in subsurface oceans on rogue planets. Life in the twilight zones of eyeball planets. Life on water worlds with no land. Life on mini-Neptunes with thick hydrogen atmospheres and exotic chemistry. Life adapts. Earth life colonized every niche from deep sea vents to upper atmosphere. Extremophils thrive in boiling acid, Antarctic ice, deep rock miles underground, toxic waste dumps. If life can adapt to that diversity on one planet, why couldn't it adapt to the diversity of planets in the galaxy? We're searching. Biosignatures, oxygen, methane, phosphine, dimethyl sulfide, atmospheric disequilibrium, anything inconsistent with abiotic processes. James Webb searches exoplanet atmospheres. Roman will study thousands more. Extremely large telescope will get spectra of potentially habitable worlds around nearby stars. We're looking for chemistry that screams life, and if we find it, everything changes. If biosignatures on even one exoplanet confirm life beyond Earth, it means life emerges wherever conditions allow. It means the galaxy is full of living worlds. It means intelligence might not be unique. It means we're part of a biological cosmos. That's the stakes. That's why we catalog every weird planet. Each one tests the boundaries of what's possible. Each one reveals formation pathways that could produce habitable worlds. Each one expands the parameter space for where to search. Here's the final piece of data that reframes everything we just covered. The formation model from Isidoro's team predicts up to 1% of super-Earth and mini-Neptune systems could host Earth-sized planets in habitable zones that formed via late giant impacts, similar to our moon-forming event. Well, 1% doesn't sound like much until you multiply it by how many super-Earth and mini-Neptune systems exist. Those planets are the most common type in the galaxy. If super-Earths and mini-Neptunes comprise half of all planetary systems around Sun-like stars, and Sun-like stars number around 40 billion in the Milky Way, then 1% of half of 40 billion is 200 million potentially Earth-like planets in habitable zones just in our galaxy. 200 million chances for Earth analogs. That's not counting M-dwarf systems. That's not counting water worlds. That's not counting subsurface ocean worlds. Just rocky planets in habitable zones around Sun-like stars from the one specific formation pathway they modeled. The actual number is likely higher because multiple pathways produce rocky, habitable zone planets. Every weird planet in this catalog points toward that conclusion. The universe makes planets promiscuously. It makes them everywhere stars form. It makes them around dead stars. It makes them without stars. It makes them from every available material in every possible configuration that physics allows. Rocky, icy, gassy, puffy, dense, molten, frozen, diamond, carbon, water, lava, stripped, inflated, migrated, ejected, captured, circumbinary, resonant, eccentric, circular. The diversity is the point. The universe is not economical. It doesn't stick to one template. It experiments. And somewhere in those 200 million Earth analogs, or billions of water worlds, or trillions of rogue ocean worlds, life finds a way. The weird planets aren't weird. They're normal. We're still learning what normal means.